You're such a good class. You quieted down so nicely there. Good evening. I've come to think that all scientific lectures should start exactly like that. I feel like it opens your mind. It was really beautiful. Thank you. So if you weren't here last week, or 2 weeks ago rather, let me introduce myself. My name is Michael Blanton. I'm the new director of Carnegie Science Observatories. In the past, you would have seen John Mulcahy up here. He is here somewhere. Can't really see the audience, but I'm sure John is here. And he held this position for many years. And in fact, he was the originator of this lecture series 24 years ago. And I've been, along with inheriting all the amazing stuff at the observatories, I've inherited this. And so I'm very grateful for that. I would also like to thank Erica Clark, who has been running this lecture series for about the last 10 years. She is, in fact, the one responsible for the musical, introducing the musical introduction. The financial support for this series comes from the Norris Foundation, and so of course we thank them for their continued support over the years. And the Huntington, the Carnegie Observatories in the Huntington have a long relationship. They actually store many of the Carnegie Observatory's historical papers, and we're really happy to partner with them on this series as well. This fits into one of their missions, which is to inspire creativity and create transformative experiences, which is the kind of experience you're having right now, in case you didn't realize. I would also like to thank the volunteers. The people checking you in, standing outside. These are volunteers from the Huntington and from Carnegie. There are astronomers, other staff members, and I want to thank them because they're very enthusiastic about this and help really make this thing happen. Thank you. So, tonight we are going to hear from Dr. Anat Shahar. She is at the Earth and Planetary Labs in Washington, D.C., another division of Carnegie Science. And I have been at Carnegie Science since January. Anat has been with Carnegie Science a lot longer. She originally got her bachelor's and master's degree in engineering at Cornell University, the same place I got my degree in engineering, so it's the best engineering school in the world. I don't think anybody in this zip code will disagree with that. Then she got her PhD in geochemistry from UCLA, and then she went to Carnegie as a postdoc and has been a staff member there for many for many years. She is now helping to lead the Carnegie Science as its Vice President of Research. She works on geochemistry. She did a lot of work on metal silicate differentiation, which I believe, I'm not an expert in this, but I believe is sort of related to how the core of the Earth formed, because iron and the crust and mantle are more silicate. No geologists in the audience. That's good. But today she's going to tell us about the origin of water, which, as she knows since she was at UCLA, is a bit of a political issue around here, but she's going to be looking a little further back in time. And I'm going to ask Anat to step out now, and we can introduce her. Oh, there we go. Thank you.
Thanks so much, Mike, and thank you, Pinyi, wherever you are, for that amazing music. I was listening to it backstage. Thank you all for being here. So as you watch this NASA video of all the planets that have been discovered outside of our solar system, the so-called exoplanets. There it goes. I want you to think about what amazing scientific moment we are in right now. In 1990, when this video begins, there were no known planets outside of our solar system. So there were 8, 9, depending if you counted Pluto back then. And since then, in the 3 decades since then, there has been tremendous scientific discovery. There are now thousands of exoplanets that have been discovered by scientists. Every single one of these planets was discovered, and you can see that over time, it gets faster and faster and faster, right? We've gotten better at this. And you'll see soon, right over here, that's the Kepler mission that specifically was looking for exoplanets in one part of the galaxy. And you can see that it found a lot of them. So as of the early 2020s, there were about 5,000 exoplanets. And as of last week, there are more than 6,100 discovered exoplanets. It's thought that every star in the sky has planets around it. So statistically, that would mean there were probably about billions of habitable planets in the galaxy. So when I look at this as a planetary scientist, I want to know, is there life on any of these planets? Are any of these planets habitable? And how would we know where to look if there are so many planets? And if we knew where to look, what would we even look for? And these are the questions that drive some of my research. So let's start from the beginning. What makes a planet habitable? Now, this is a very different question than asking, what is the origin of life? The origin of life question is a question about taking non-living matter and turning it into a living system. It's a prebiotic chemistry question. Whereas what makes a planet habitable is more of a solid planet question. What is it about a planet itself that can host and sustain life for long periods of time? What are the characteristics of a planet that can host life? So it's not about the living system, it's about the planet itself being ready for that living system. Now, I tell you all this while I show you an image of Earth. And on some level, that's not super satisfying, right? On some level, you don't want to hear that we're looking for life that's exactly like life on Earth, because who knows what kind of life there might be. On the other hand, we have an n equals 1. We have one planet we know of that hosts life and sustains life. And so it would be kind of silly to not get some clues from Earth in order to understand what it is about Earth that allows it to be habitable. What is it about Earth? What are the characteristics of Earth that have allowed life to be hosted and sustained all this time? And so the first is a magnetic field. A magnetic field shields our surface, life, from really harmful radiation, from cosmic rays and from solar wind. It also protects our atmosphere from blowing off into space, and it's necessary for life as we know it. Now, the magnetic field is generated deep inside a planetary interior. So as Mike was just saying, core mantle differentiation, right? So the core of the planet, the metallic portion in the center of the planet, is what allows there to be a magnetic field. Now, a second characteristic of Earth that allows it to be habitable is plate tectonics, what we call plate tectonics, right? So that basically just means the recycling of nutrients, the replenishment of nutrients on the surface of the planet. Without that, there would be no more nutrients. We would kind of use them all up and there would be nothing new. So this exchange with the interior and exterior of the planet is really important for life. Plate tectonics also modulates our climate at the longest timescales. And lastly, there's my favorite, which is liquid water. Astronomers will tell you that a planet is habitable if it is in a zone where liquid water can exist. NASA has told us for a long time that its mantra is follow the water. And there are reasons why this is all true. The reason is that water has this really funny shape. It's got this asymmetrical shape, which allows it to be what we call the universal solvent. It can dissolve molecules and nutrients really, really easily, unlike any other liquid, unlike any other solvent. And it can also bring nutrients into cells, and then it can excrete waste out of cells. So it's got this beautiful ability to do all these things. Now, life on Earth has been found in places where there's no sun, where there isn't free oxygen, but never in a place where there's no liquid water. So that tells us something. So what I'm trying to argue to you so far is that in order to really know if a planet is habitable, what we really need to know is about the planet itself. It's about the interior of the planet, what's happening inside the planet. So what you see here on the left is a habitable planet, right? It's a planet where plate tectonics stabilizes the surface climate, cools the interior so that the magnetic field can be generated, and then it shields the surface from water loss. On the right, we have what we call a stagnant lid planet. This is a planet that has no plate tectonics, so the lid is completely solid, and so nothing cools on the interior of the planet does not cool, no magnetic field is generated, and the surface gets really, really hot and dry because there's no magnetic field, water can just be lost into space. And so you see, in a very simplified form, that it really is the interior of the planet that can really tell us a lot about whether or not it's habitable. So if we're looking for a habitable planet, and we want to know which planets could possibly host life, one of the questions we really have to ask ourselves is, where does a planet get its liquid water? Where did Earth get its liquid water? So let's go back and try to figure out what we know about liquid water on Earth. In the classical model, like this one, what you see is planetesimals, okay, close to the sun and further away from the sun. This is Jupiter. And what you see is that the red ones are hot and dry because they're close to the sun, and there's a thermal gradient moving away from the sun, where as you move further and further away, things get wetter and cooler. But as things start to bounce around and collide with each other and mix, what you see is that some of that material from further out in the inner solar system goes into the inner solar system, and everything kind of mixes and becomes wet. So this is one idea of how Earth got water, that there were a lot of planetesimals around when Earth was accreting, and some of them were wet and they were further out, and they kind of collided with the planetesimals that made Earth, and everything kind of ended up a little wet. Another model is similar, except that it takes the wet material and pushes it further out in the solar system. So instead of being within the first 5 AU, we're now looking at like 5 to 15 AU further out. So this is the wet stuff, and this is the dry stuff. And I don't know if you know that there's this model that Jupiter and Saturn were not always in their current locations, that they migrated into the inner solar system and then back out. And if that's the case, then when they migrated back out, they scattered all the material in the outer solar system, all the comets, all the asteroids that were wet in the outer solar system, pushing them into the inner solar system. And then what happened in the last video happens again. Things start to mix all together. So these are kind of the ways that people thought that, or think that Earth got its water, from asteroids and comets, when we look at it from this dynamical point of view from the outer solar system. Another way to look at this is to actually measure a sample, okay? So an astronomer or a dynamicist might do it these previous ways, but a geochemist or a planetary scientist might do it this way, where you can actually measure a meteorite that fell to Earth and see how much water was in it and what the tracers of that water is. What are the isotopes of that water, the deuterium to hydrogen ratio? Or you can go to a comet, such as this one, Comet 67P, that the Rosetta mission went to, where they could measure, again, the water content of these comets. And what they found is that they can find similar isotopic ratios, similar deuterium to hydrogen ratios between these materials and Earth. And so if we put all this together, the common theory or the common understanding of how Earth got its water is that it came from comets and asteroids from far out in the solar system that then mixed twice. Once when the Earth was accreting, and then once again later after the moon-forming giant impact, when Earth got a little bit more water for the oceans that has the same isotopic composition as these materials here. But there's a problem with that. And the problem is that's kind of lucky, right? We're kind of lucky that Earth was in the right place at the right time with the right proportions of the right meteorites and the right comets and the right asteroids, and it all kind of came together perfectly at the right exact time. And why didn't that happen in all the other planets, right? Why isn't there water everywhere if this were the case? So my colleagues and I decided that we didn't love this suggestion or hypothesis, and so we wanted to try something different. But in order to do that, we wanted to look at the planet as a whole, right? The whole planetary formation process, and ask ourselves, is there a time during the planetary formation process with which water can be delivered to a planet, or accreted onto a planet, or somehow formed on a planet? So let's talk about planet formation. So when planets first form, there's a disk of gas and dust that rotates. That disk is 1% stuff and 99% hydrogen and helium. Now, the majority of that disk becomes the sun, the star in the center of the solar system, and the rest of the stuff becomes the planets. In the canonical way of looking at planet formation that we learned by studying our planets, our terrestrial planets, you have the terrestrial planets form after the gas giants form. And so by the time the terrestrial planets form, this gas-rich disk of hydrogen and helium is gone. Then after some time, the planet gets to a size where it can heat up and it becomes completely molten. And then it does that thing that Mike was talking about. It differentiates into different layers. It separates into different layers. You have your core in the middle, your mantle, and then your crust. So this is your typical planet formation process. And so the question is there a time during this planet formation process when we could look for water formation? And when we only think about our solar system planets, it's kind of hard to think of any moment where that could have happened, other than the hypothesis I already told you. But like I showed you on that first video, we now have 6,000 other planets to look at. Not 8, but 6,000. And so that's pretty good statistics for trying to figure out about planet formation in general. So let's talk about exoplanets for 1 second. It turns out that the most common type of planet that's been found in the galaxy is called a super-Earth or a sub-Neptune. They're very, very similar, but they're two distinct groups within the same population. And these are planets that are about 1 to 4, 2 to 5 Earth radii. They're a little bigger than Earth, but they're rocky planets. The difference between these two planets is that a sub-Neptune has a hydrogen-rich atmosphere surrounding it, and a super-Earth does not. And so if you look a little closer at what these planets look like, you see that there's this weird bimodal distribution. There's a lot of sub-Neptunes, rocky planets with a hydrogen-rich atmosphere, and there are a lot of super-Earths, rocky planets without the hydrogen-rich atmosphere. But there's not much in between, and that's kind of weird. You would think that planets kind of have this gradual with mass, right, that you would just find all sorts of different masses. But there's this weird, what astronomers call radius valley right here. And so what astronomers tell us is that actually these were all the same population of planets. They all were like this. They were all rocky planets with hydrogen-rich atmospheres, but some just lost their hydrogen-rich atmospheres for all sorts of different reasons. So that's interesting. If the most common type of planet in the galaxy was once a rocky planet with a hydrogen-rich atmosphere, why couldn't our planets have formed with a hydrogen-rich atmosphere? Because that's not what we were taught when we were in graduate school. So let's think about it. Maybe that's a possibility. So what would that mean? It would mean that when the terrestrial planets formed, they accumulated some of that gas that was still around from that original disk, from the solar nebula. So they must have formed a little quicker than we previously thought, which doesn't seem like that big of a deal. So if that's the case, what would that mean? Importantly, that would happen at a time when the planet was completely molten. So I have 2 teenagers at home, so I call this the teenage stage of planet formation. It's extremely dramatic, right? It is literally the most dramatic time that you have in a planet formation process. The entire planet melts, everything starts shifting around, the chemistry changes drastically, and depending on what happens during that time, the evolution of that planet can go in all sorts of different directions. And so if we take this magma ocean stage, we call it, and we surround a planet during that stage with a hydrogen-rich atmosphere, what happens? We have no idea. And so this is a perfect thing to do in science. When you have no idea what's going to happen, you just try it, right? So the first thing we did is we tried to look at this theoretically. So the first thing to ask ourselves is, well, what size does a planet need to be in order to hold on to that atmosphere? You can imagine that when a planet is too small, it doesn't have the gravity to hold on to an atmosphere. And so we took, this is a plot of surface temperature, the temperature of the surface of the planet, as a function of the mass. So Earth, as a function of Earth mass, right? So Earth would be here at 1. And what you see is, in this shaded region, is how big a planet has to be in order to hold on to its primary atmosphere. If it's too small, then it doesn't have enough gravity. And if it's too big, and if it's big and too hot, it radiates that atmosphere off. And so that atmosphere doesn't stay. But in this region, you can hold on to a primary atmosphere. And it's in this region that Earth's planetary embryos were. So theoretically, Earth could have held on to an atmosphere when it was still in a molten stage. If you're curious about a planet like Mars, for example, it technically is big enough to hold on to an atmosphere, but by the time it got to that stage, it was too cold to be in the magma ocean part of its planet formation process. So then it doesn't interact with the atmosphere, right? You need to be hot magma in order to interact with the atmosphere. You can't have a solid surface. Okay, so now we have all the building blocks. Let's see what happens. So we take a magma ocean planet and we surround it with a hydrogen-rich atmosphere. What happens when you surround it with a hydrogen-rich atmosphere is it acts like a blanket. It slows down the cooling of that magma ocean by a factor of 10 to the 6th. So that planet could be molten for tens of millions of years. And there's a lot of chemistry that can happen in tens of millions of years. So we literally took 18 equations. I know that doesn't seem like Earth can be told or explained in 18 equations. I understand that. However, it's a good place to start when we didn't really know what to expect. So we took 25 components, 25 different elements that we know are the most common in a planet, or molecules, and we just solved for these 18 equations. We solved thermodynamic equilibrium, which basically just means what is your happy place, right? Just run the equations and see kind of what pops out. And what popped out is a tremendous amount of water. So why is that? So the first thing that happens is that hydrogen goes into the metallic portion of the planet. Silicon goes into the metallic portion of the planet, and oxygen go into the metallic portion of the planet. And when these elements go into the metallic portion of the planet, they release other elements. So for example, when silicon goes in, it releases oxygen. And when the hydrogen in the atmosphere sees that oxygen, it forms water. When hydrogen interacts with the FeO inside of a silicate mantle, so all mantles have iron oxide in them. Our current mantle has 8 weight percent, for example, iron oxide. So when hydrogen interacts with that FeO, It forms iron metal, which then goes into the core, and water. All these different equations form water. So if you start with a completely dry embryo, you don't need any asteroids or comets or anything to hit you, right? You end up with a very wet planet. So if we take Earth and we surround it with a hydrogen-rich atmosphere, or proto-Earth, I should say, we can explain Earth. So that's great, except for one thing. I'm an experimentalist. I'm not a theorist. And I love theory, and I love equilibrium thermodynamics, and it's all wonderful. But without the experiments proving that you're right, it's really hard to really believe that that is all correct, at least for me as an experimentalist. And the one variable that we don't know is actually how much hydrogen goes into a magma ocean. So everything I just showed you is theoretical. We can calculate how much hydrogen we think goes into a magma ocean, is what we call soluble in a magma ocean, but we actually have no idea. That number just doesn't exist. It has never been experimentally determined for these sorts of conditions. And so that's what we set out to do. And this wonderful human was a postdoc in my lab at the time. And she took on this project, and you'll see that it was no small thing to do. And so here's what we wanted to do. We wanted to basically take the same idea, a hot magma ocean, surround it with hydrogen gas, experimentally in a laboratory, and see if we formed water. So how do you start this? Well, the first thing you need to do is you need to make the starting materials. Now, making the starting materials normally in a lab is not hard. You take a bunch of oxides, you take, little pieces of rock, whatever you want, you melt it in a furnace, and there you have your starting material. Except when you're looking at hydrogen dissolving into a glass, you can't have bubbles in your glass because it makes it easier for the hydrogen to get into the glass. So you need to create a bubble-free silicate glass, which is very hard to do. So we had to travel to Paris to do this, which I know is really, really tough. Yeah. So there's this wonderful lab in Paris at IPGP, and there's this machine, or this instrument, called a laser levitation furnace, or an aerodynamic levitation furnace. What you see here is a hot magma ocean, right? So this is a tiny little sphere of glass that's being heated with a laser while levitating in a gas so that it doesn't touch the nozzle of the actual experiment, so that it doesn't get contaminated. And you can see the laser was heating the silicate glass at about 1900 Celsius. So this is how we make our starting materials. We then take this material, we cut it into a very thin wafer, and now we have our what will be our magma ocean. Okay, this is the same composition as what we think the Earth's magma ocean is. So then what do? Well, these conditions in early solar system history were really hot and very high pressure. And so we use this thing called a diamond anvil cell. That's a picture of it. This is the actual size of it, okay? So this is that whole thing right there. On the left, obviously, the diamonds on the right are highly out of proportion. So what we do is we take that thin wafer, we put it in between two diamonds that have culettes, so it would be that part, right, the tip of the diamond, that have a tip that's approximately 200 microns, so that's 10 to the minus 6. And then we surround it with hydrogen gas, and then we squeeze it. And then when we squeeze it, we increase the pressure. Now, the way that we do that, and the reason that it works so well, is that pressure is force over area. So you can increase the pressure a lot when your area is really, really small. Okay, so the area between the diamonds is quite small. And then to heat it up, we shine a laser through it. Diamonds are transparent to laser light. So the laser goes right through the diamonds, and it couples with the sample. It couples with the sample here. Okay, so now we have high pressure, high temperature, of a very, very tiny little sample. So what does this look like in real life? Here's a blown up image of what it looks like when you look through the diamonds. Okay, so you can look at it with a microscope because it's optically transparent. That thing right there is that silicate wafer that we made. And all the stuff around here is hydrogen gas that's slightly compressed, so it doesn't look like a gas, but you can see it. And then after the experiment, it looks like this. So this experiment was done in an argon-hydrogen mixture. We use a mixture of argon and hydrogen because if you use pure hydrogen, the hydrogen likes to diffuse into the diamond and it cracks it into lots and lots of pieces. And that's not fun. So we use an argon-hydrogen mixture. And then this experiment was done at about 4,000 Kelvin, a little higher, and 35 gigapascals. 35 gigapascals is 350,000 atmospheres. Okay, so it's a lot. It's high pressure. Okay, so now we have this tiny little sample that we can hardly see, that we increased the pressure and temperature. We wanted to see what happens between the hydrogen atmosphere and this magma ocean. Now what do we do with it? Well, the first thing we do with it is we have to cut it, because when it comes out of the diamond anvil cell, it's like this, and we want to look at it like this. We want to see the cross-section of the experiment. So we use what's called a FIB, a focused ion beam, which is literally a focused ion beam. Okay, so it hits the sample, and it cuts the sample with an ion beam that's focused. And so what does that look like? This sample is in here. This is a piece of dust, okay? There's just so much that one can clean something. And so these are orientation marks to show us where we are and where we want to cut. So this is the sample chamber in here, and you can see the scale bar here is 10 microns. This is what it looks like after we've milled it, after we've cut it on both sides, okay? So if we look at that another way, this is that same image I showed you before, and just for scale, this is a human hair, just so we know about the length, you know, how big we're talking about here. And this is as you start milling. So this part is in here, okay? And you keep milling and you keep milling until you find the sample, right? There's the sample, you can see it. And so you do this on both sides. So you can see here it was cut on the other side as well. Then you cut here, and then you attach a needle to this, and it just sticks from electrostatic forces, and then you put this on a piece of foil on its side so that you can then analyze it. It is very, very stressful. That's why we love our postdocs so much. Okay, so then what do? Then we look at what we found, right? What did we see? So this is a chemical map. You can do chemical maps of what you're looking at. So what you see here, here's the sample. This is iron, oxygen, silicon, calcium, magnesium, and aluminum. So the first thing you see is that the major elements here all kind of correlate with one another. And that's just telling you you have a silicate, okay? These are the normal elements that you would find in a silicate in a magma ocean. But then you have this like chunk of iron right there. Now, we didn't put any iron metal into our experiment, right? So what is this chunk of iron? So now if we look at it in this way, just with regular light, you see that there's this like blob of iron. And here it is even bigger, right? And here's a different experiment. You see it again. And it's got all these tiny holes in it, right? So what are these holes? What are these bubbles? So the first thing we learned from this experiment is that we formed iron metal. Why did we form iron metal? I'll tell you in a little bit. But the second thing you can see from the iron metal is that it has the holes. And the holes, we think, if you remember when we did the theory, we found that hydrogen enters the iron metal in the core of the planet. So we think that these bubbles are hydrogen that when we quench the sample, when we take the sample out from high pressure and temperature, the bubbles, the hydrogen dissolves, it comes out of the iron metal. And so that all these little bubbles are telling us that there was hydrogen inside of this metal. The next thing we found are these weird voids, these weird holes. So it says that they're resin filled because in order to take the sample out of the diamond cell, we had to fill it with a resin or else it would all fall apart. So if there's just resin, it means that that region was empty. Now, you see how big that region is, right? You can't even see the diamonds from where you're sitting probably, but it's quite small. If you took 40 elephants and you had them stand on your fingernail, that's about the amount of pressure that we put in between those diamonds, okay? How could there possibly be empty space in a situation like that? I mean, logically, that makes absolutely no sense, right? It's impossible to think that with that much pressure on such a small area, you would have empty space. So what do we think was in that empty space? Water. And why did we lose the water? Because when you take the sample apart, you're talking about a tiny, tiny little droplet of water that would have been there. It would just disappear. We would not see it. So that is our current thinking. I'll give you a little more detail in a second. But then the other question we had to ask ourselves is, did we get any hydrogen into the magma ocean, right? That was kind of the point in the beginning. It's great to form water. That was another part of the question. But also, did any hydrogen itself get into that magma ocean? And so for that, we need a different instrument. We need an instrument called a nanosims. And a nanosims is a way of making elemental maps, like imaging, of tiny, tiny little samples of the nanoscale, right? So the first thing we looked for was silicon. This is a silicon map. And what you see in the sample is that it's pretty homogeneous. There's nothing extraordinary about it, and that's kind of what we expected. But then if you look at the hydrogen map of that same portion, you see this hotspot, okay? So there's hydrogen, H2 or some form of hydrogen, that has a hotspot exactly where we heated the sample during the experiment. And so how much water? About 6 weight% of water. To put that into perspective, it's about 2 orders of magnitude more than we expected to see. The reason we used the instrument that we used is because it's really good at detecting tiny, tiny amounts of water. This was almost too much for the instrument. It almost saturated because it was so much water that they found within this sample. This is our starting material, just to show that we don't find water everywhere, right? So our starting material didn't have any water in it. And then we looked at this as a function of pressure and temperature for a bunch of different experiments, and we found that it's really a function of temperature. So if you stay at one pressure and you increase the temperature, you will increase the hydrogen content significantly. And so temperature is hugely important when it comes to the amount of water or the amount of hydrogen that you can put in this magma ocean. Okay, so what does that all mean, right? Those are the experiments, and they were amazing and fun and stressful and crazy to do. But what does it mean now that we have the results? Well, we think there are 2 processes occurring at the same time. One is the dissolution or the solubility of H2 from the atmosphere dissolving into the magma ocean. The other is what we also showed in our theory paper, where you have H2 interact with the FeO and create iron, metal, and water. And that's what we found in our first 2 results, right? We found iron, metal, and we found these voids that we are interpreting as having had water in them because it makes sense in this scenario. And so we found that our theory was correct, which is wonderful, but also this part we did not know theoretically, and now we have a number for how much hydrogen can dissolve inside of a magma ocean for a given planet. So what that means for planet formation is that if you have a small planet that, let's say, gets hit by an impactor, right? And it forms what we call a magma pond, as opposed to a magma ocean, and there's hydrogen around, you can get hydrogen gas hydrogen into your magma ocean and form a little bit of water. But if you have a big planet, then you can form tons of water during that planet formation process. And so you form water that goes into your mantle, it goes into your core. You can form water vapor because you have so much water around that some of it likes to be in equilibrium with the atmosphere. So there's water vapor in the atmosphere as well as water inside your system. And then something I didn't tell you that we found in our experiments is at these highest pressures. So at the highest pressures, we have something very strange happen. So if you've ever made salad dressing, you know that when you take oil and vinegar and you mix them together, they don't really like to mix so much, right? They kind of stay separate. But if you add mustard as your emulsifier and you shake it, it kind of turns into one phase, right? So you have your two different phases, but then once you add that emulsifier, suddenly you just have one phase. You have one salad dressing. It's not separated anymore. The same thing happens here. Water acts like the emulsifier between the silicate and the mantle. So at the very highest pressure experiments that we didn't find metal and silicate and water. We found a very strange mixture of one big phase that is what we call miscible, meaning that they're not different phases anymore, they're one phase. So some of these biggest planets that we might find, or that we have found, could possibly not even have a metallic core and a silicate mantle and water. They could just be one odd phase that we don't really know much about. So this is the topic of a lot of further experiments for sure. But really what we're finding is that you can form water, you can dissolve hydrogen, and depending on the size of the planet and the evolution of the planet, it will look differently depending on the actual planet. Now, I showed you theory, and I've showed you experiments, which is my expertise. But one of the things that we try really hard to do in my group and with my colleagues is we try to do things in three different ways. We try to do them theoretically, experimentally, but then also observationally, right? It'd be one thing to only see something in the lab, but you kind of want to see it in nature, too. You want to see that what you're saying is also real. And so how do we look for this in nature? Well, the only way that we can really look at exoplanets in this sort of way is by looking at their atmospheres. And so there are plenty of amazing scientists at Carnegie and elsewhere that have JWST data and time on JWST to get data to look at atmospheres of exoplanets. Now, atmospheres are complicated because they don't just tell you about what's happening that minute on the exoplanet, they also tell you about its past. They tell you about what had happened in the past, right? Just like I just showed you. If in the past you put a ton of hydrogen into your mantle and it comes out, that will come out into your atmosphere. And so your atmosphere is telling you that at some point there was water around in the interior of your planet. And so we have lots of wonderful colleagues that look at these atmospheres. And some of them, just a few months ago, found a planet. Astronomers love to name their planets, but I never remember the names, so I won't even try. That is a super ultra-hot super Earth that is a magma ocean planet surrounded with an atmosphere, which is not exactly what we found because this is a secondary atmosphere, not a primary atmosphere, but it tells you that inside that magma ocean, there were volatiles that have now come out into that secondary atmosphere. So now we have observational evidence, experimental evidence, and theoretical evidence, all telling us very similar things. But I wouldn't be, dare I say, a great Carnegie scientist if I didn't also want to do something crazy and different. And so my next step is to design a mass spectrometer, a new type of instrument that does not currently exist. The thing that you see here is just an image, a design, and it would basically take up this entire stage if it were here right now. And the goal of this instrument that is being designed with the help of NASA is to do those same experiments, but not in the diamond anvil cell where we have high pressure, at room pressure, but at very high temperature. And the goal is to basically do the experiment of a magma ocean planet where we can change the atmosphere around that planet, and then we can detect all the gases that come off and then compare those to the JWST spectra. So this is our way of being able to understand all the different spectra that are coming from these different exoplanets. So this will be online hopefully in like a year and a half or so. Okay, so where does liquid water come from? So I hope I've shown you, somewhat proven maybe, that, that water is formed typically during planet formation processes. And the only reason we were able to even think about doing this sort of research in the Earth and planetary sciences is because we have colleagues in astronomy that tell us all about exoplanets. And so this is a really great example of how we, as scientists, have to talk to people in other disciplines and get ideas from people in other disciplines. Because if you had told an Earth scientist that it's possible that Earth was formed when there was still the solar nebula around, they would have told you were crazy. But once we started getting all the data from our astronomer colleagues, it suddenly didn't seem as crazy. And so I would argue that water is ubiquitous and that many of those planets, I won't say all because that's silly, but many of those planets that you saw in that very first video likely had the potential to have liquid water, depending again on their exact trajectory. But in terms of the planet formation process, it is easy, I think, to form water. And while we can't say that Earth didn't get its water from comets and asteroids, we can't really argue against that. We can say that it's not necessary. And with that, I thank you for your time.
That was great. So there is a microphone over there. There is a microphone over there in between the orchestra and whatever's behind the orchestra. And so if you have questions, go there. In the meanwhile, I want to remind you that the next of these lectures is in 2 weeks, which is March 30th. Thank you. From Andrew Robertson, who's going to talk about dark matter. And yes, dark matter. Which did not form in the same way that water did. And the tickets for that will go on sale tomorrow morning at 10 a.m., I believe. But now we're going to alternate, and we're going to start on my left.
Oh, boy. One of the reasons for pegging comets as a source of water is the isotopic ratios, which you did not address here. Is there a way to work isotopic ratios into what you're doing, and will it take another half hour to explain it? Thank you.
I could not have planted a better first question. So I am an isotope geochemist, and my specialty is isotopes. And this is my favorite question, because when we tried to publish these, the first theory paper, the reviews we got back were only about isotopes. And so it's a really good question. So here's the idea. So the reason, like you said, that the number one reason that we think the Earth got its water from comets or asteroids is because of the D to H ratio, the deuterium to hydrogen ratio of our oceans and of these, in particular, carbonaceous chondrites, right? Meteorites that we think were the building blocks of Earth. And they have a very similar isotopic composition. And so it's very hard to argue against that, except Mike mentioned that I've spent much of my career learning or researching planetary differentiation. And it turns out that when a core and a silicate separate, if that hydrogen, like we think happens, goes into the core of the planet, it actually leaves behind a huge isotopic fractionation in the D to H ratio. And so we shouldn't expect, actually, that the building blocks of Earth have the same isotopic composition as the mantle of the Earth or the oceans of the Earth, we should expect them to have the same isotopic composition as the bulk Earth. And so currently, and these are very hard experiments to do, I would say they are like my holy grail of my career, but there is a group in Japan that has tried to do these experiments, and the reason it's so hard is because as soon as you take the pressure and the temperature off of the sample, the hydrogen diffuses out of your sample very, very quickly. And so what they've done is they've taken this diamond cell and they froze it. They put it in a cryo, and they do the experiment. After they do the experiment, right, they freeze it, and then they take this and they put it into the nanosims, that instrument I showed you, frozen so that the hydrogen does not diffuse. And their preliminary results agree with our results. Thankfully.
Let's go over to the right.
Assuming it came mostly from hydrogen entering the magma ocean, have you back calculated, given that we know how much water we have and water vapor we have around the planet, how much hydrogen would you generate, and does that make any sense based on observations?
Yes, so it all is, it's very much a function of the temperature. And so in that original theory paper, we pin it down, when it just goes through thermodynamic equilibrium, we end up with about 2 Earth oceans worth of water, which makes sense because we have one on the surface and then we think we have some in the interior as well. So you can make the right amount. Now the big question is how much hydrogen is in the core of the planet, because hydrogen loves iron metal. If iron metal is around, it will just iron metal loves hydrogen. So if hydrogen is around, iron will just soak up that hydrogen a lot. And so it's possible that the core of the planet is actually the biggest sink of hydrogen that we have, in which case you would need more than 2 oceans worth because you would need to account for that as well. But it's all a function of the temperature, of exactly the temperature that this happened, and you can make it work pretty easily with the math.
Okay, great, thank you.
Yeah, thank you.
Fascinating, fascinating talk, and I really like the experimental side of the equation that you're doing, your three-legged stool.
Thank you.
I guess my question has to do with time and the scale of time. In order for an experiment to be done in our lifetime, it has to happen on a pretty fast scale, universe-wise. And so I'm wondering, if you do these conditions, how quickly would you create that much water? I mean, if you can measure the water you're making in a very small space within a few days experiment, does that mean that this ocean of water happened in a few days?
That is a great question. So I'll start by telling you that our experiments last on the order of nanoseconds, because you can't heat at those conditions with a laser for a long time before it really doesn't like it, and the diamonds start doing all sorts of crazy things. So the experiments are super short. But your question is a good one in the sense that I had not thought about how long that would take on a planet, other than knowing that when the hydrogen-rich atmosphere is there, it has tens of millions of years in order for this to happen, which we think is plenty. Now, why do I think that's plenty? I don't know. It just seems like a really long amount of time. So I don't have a great answer for the kinetics portion of it, because you're right, I can't do that in the lab. But I can think about how to, I don't know how to answer that. But I think tens of millions of years is enough.
Thank you.
It's a good question.
Thank you for your lecture. 2 weeks ago, when I got the title of it, I submitted it to Chat GPT and got a very respectful analysis of what you presented. Okay. And Chat has a question for you.
This is the first time this has ever happened to me. Okay.
Okay, here we go.
Here we
This
go.
is Chad's question.
Okay.
If hydrogen dissolves into magma oceans and forms water, are there isotopic fingerprints in mantle materials that uniquely identify this process compared with water delivered by asteroids?
So that adds to the question you asked. And so I have thought about this, thankfully, and the way to answer that question is to look for an isotopic signature of the solar nebula. So we talked about isotopic signatures of chondrites, right, of meteorites or of comets that could have hit the Earth being the same. But if what I just told you is true, then the Earth should have the same isotopic composition as the solar nebula, because that's the hydrogen that we took in the beginning. But again, because Earth has gone through so many different processes that have fractionated, that have changed the isotopic composition of the hydrogen, it's very, very hard to do this. So I'll give you an example. Venus. Okay, Venus is more like a stagnant lid. It was more like that dead planet that I showed you in the beginning on the right that doesn't have plate tectonics. Or so we think, right, until NASA sends more missions to Venus, or ESA. If you look at the isotopic composition of the water vapor in Venus's atmosphere, it's highly fractionated. And the reason that it's highly fractionated is because it's thought that Venus lost a lot of its water because it didn't have that strong magnetic field and it didn't have plate tectonics and all these other things. It has lost a lot of water. And so because of that, the water vapor that's left is highly fractionated. When isotopes fractionate, they fractionate as a function of mass. So what I mean by that is the isotope, the element that's the easiest to change, is hydrogen because it's the lightest. So while, as an isotope geochemist, I think isotopes are really good tracers for all these different processes, I think when it comes to hydrogen, we're not going to be able to answer any of these questions until we have every process that has occurred on Earth where hydrogen has been involved and the fractionation associated with it, and then we can put it back into ChatGPT and ask it what happens with all those fractionations.
We got a couple questions from folks watching online. So one is, what kind of temperatures are we finding on Earth-like exoplanets? I know you mentioned one ultra-hot super-Earth, but what else are we seeing?
Oh, that's a great question for an astronomer. I think it depends. I think they have found all sorts of different temperatures. So there are three things that you can measure, not easily because it's hard, but three things that are normally measured with exoplanets: temperature, mass, and radius. And from temperature, I think it ranges all over the place. From, it depends if you're talking about the day side or the night side, because there are exoplanets that are tidally locked to their stars. So on the day side, you could be, thousands of degrees, whereas on the night side, you can be, 20 Kelvin or 100 Kelvin or something. So it depends. There have been all sorts of temperatures that have been found.
And really quickly, someone asked, does a layer of carbon change how oxygen is formed?
A layer, I don't know what it means, how oxygen is formed, but I will say that carbon is our next set of experiments. What happens if we now add carbon to the system? I have no idea what happens. Nobody has any idea what happens. I will let you know next time.
Well, that seems like, oh no, we got more. Okay.
Yeah, thank you. So an Earth-like planet can generate its own water, so to speak. Does that mean that the original solar nebula wasn't full of water that condensed on its own in the outer planets?
So there was definitely, it's called the snow line, the area where ice and water can condense. And it depends on how far you are from the star, from the sun. And so, yeah, past the snow line, there was plenty of water around. And that's what those original videos kind of showed, is that area was very, very wet. And so water is not something that we lacked, back then.
Thanks.
Yes. Oh, one more. Yes.
You said whenever examining the samples of the sliced iron after compressing it, you found the holes in it that you theorized contained the hydrogen, right?
Yeah.
What happened to them is they just sort of evaporated and disappeared as you cut them open, so you couldn't find them?
Yes.
Have you tried using extremely low temperatures to try and preserve them as crystallized ice form to keep them from disappearing or moving?
Yes, so that group in Japan that I was referencing, they do that. But I don't know if any of you listened to Science Friday, but I talked to Ira Flato about this exact thing 2 weeks ago on Science Friday because there was a new paper that just came out that didn't use the cold technique like you just mentioned, because it is quite hard to do that. But they used a different technique called an atom probe. And what it does is it basically looks at a very, instead of cutting with the fib into a wafer, you cut into a needle, and then it kind of bombards the sample, and it's able to look at the chemical composition. And by doing it that way, they were able, because you can go kind of atom by atom, they were able to find hydrogen inside of that metal. So that just came out just a few weeks ago.
Thank you.
Yeah, thank you. All right.
Amazing.
Thank you.
Let's thank Anat again.
Thank you. If anybody wants to come check this out, I'll just be right here.
Good night.
Thank you.